Good day, folks. This is tutorial number 8 in a playlist which is called Dynamic Scenario and Animation Modeling with 3D Experience. In this tutorial, I would like to discuss the issue of torque law excitation. And in fact, tutorial 9 is also going to be on the same topic, but the way it is done, it's different. So let's concentrate on this particular tutorial number 8. So first of all, if you're going to use this feature, you have to create a dynamic scenario. Okay, you cannot do that in kinematic scenario. It has to be dynamic scenario. And here is the icon for it. And the problem that I'm going to do is a very simple problem because I just want to show you what the critical steps are and the features are when you try to do that in 3D experience. We have a disk with these dimensions and a torque is applied to it, and the magnitude is over there. Obviously, if there are no other uh, forces and moments, this thing starts to spin as if it was done in a free space. Okay, there is no friction, there is no other gravity, there are no external forces and moments. So this starts to spin. Now I'm going to model this thing. Then I'm going to check my results against hand calculations. Okay, they better give you the same answers. First of all, we're going to assume that this is made out of standard steel with the density given there, and based on these dimensions and the fact that G is 9.81. Oh, sorry, based on the fact that these are the dimensions and you can calculate the volume multiplied by rho, you're going to get 125.6 kilogram. Okay. Now, uh, because we're going to compare these things with analytical hand calculations, I have consulted a reference, and it gives you the mass moment of inertia about the axial direction. Z-axis is this, and in the transverse directions, which is x and y, if you look at it, it's going to be half of that. Okay. Now, notice that this is almost half of that, not quite, because the the, the 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 length direction also has an effect. Okay, so these are what we're going to be using for hand calculation purposes. I'm going to do it over a 10-second interval. Do the simulation over a 10-second interval. So let's go back to the very simple expression from your first dynamics book. So the torque applied is equal to I, because the torque is about the axial direction. It's going to be I times alpha, or T is equal to I times alpha, but alpha is omega dot, angular velocity. So out of this, if you plug in the value of T and the I axial, you're going to get angular acceleration, omega dot, of 41.95 radians per second squared. And because this is constant, if you integrate it, you're going to get angular velocity linearly changing. It's going to be this value times t. So it's going to be 41.95 times the time, and the unit of it is radians per second. All right. If you plotted the angular velocity, it's going to be a linear variation. You can see that it's multiplied by t, multiplied by time. So this is going to be a linear rise in the angular velocity. Now, just to let you know, this for comparison purposes, the angular velocity after 10 seconds is going to be this thing times 10, which is roughly 419 rad per second, which translates into 4,000 RPM, approximately 4,000 RPM. So let's go ahead actually and model this thing. And all right, here is the 3D experience interface. Let's go ahead and start with an assembly. There we are. We're going to insert only one part in this assembly, and that is the disk. Okay, right click, properties, right click, insert, 3D part, and this is going to be my disk, rotating this. Let me change the name of it. So this is I'll call it the disk. Okay, and here's the disk, and say okay. Let's go make it on that horizontal plane. I will sketch a circle of radius. Uh, Let me see what I had here. Radius 0.25, 0.25 a meter, of course, and then exit. I can't remember whether this was the radius or diameter. Let me double check on this. Oh, that's the diameter. Okay, so actually diameter is going to be 0.5, not 0.25. All right, good. Exit, and I'm going to pad it. I'll do a symmetric padding, and in each direction 0.05, which gives you total height of 0.1 because it's symmetric. Now, what I will also do is create a point, and it doesn't matter where that point is, but let me create a point up there. So for maybe I'll go in the Z direction, I'll go point 4, makes no difference, right there. And I put an axis system here. Uh, there is a reason I do that, because you have to apply the torque about an axis, and this thing, does not have any edges, straight edges. So I'm going to create an axis system at that point, just so that I can see it better. Good. Now, I will also create a point on this curve. So another point on this curve. That's where my probe is going to go. On that curve, it doesn't matter where, really doesn't matter. So it just created at that location. Good. This is my model, nothing else. So what I'm going to do is go to uh, mechanical system design, because that's where I apply my material properties and everything. First of all, this is my mechanism. Okay, so mechanism representation, good. And if you want to see what kind of a joints it has no joints at all. Okay, and I'm not going to fix this thing because this is not fixed. I mean, usually when I have more than one part, one of them I fix, but this one is it has to be rotating. All right. So here's what I'm going to do. Let's apply material to that. So here is the weight definition. Right now it's 100% is missing. So I select either this disk or that entire assembly, but really doesn't matter. There's only a single part. Click on this hyperlink to declare the weight, which means really the mass. Let me move this thing on the side. Now notice that right now it's 0. If you click on this checkbox, it's going to put properties of steel for you on that, which is the density of it is 7,770 kilogram per meter cube. But notice the weight of it, or the mass of it, 152.5. It agrees with this number. Okay, good. Let's check the different eyes here. So one of them should be 4.77. The other one is 2.55. And that is right here, 2.5, 2.51, 2.51, 4.77. So it's right there. Okay, now we're done. So we just close this thing, see the close? And we close that too. That's pretty much it. So we have applied the weight here. Now we're going to switch to mechanical systems experience. We already have a mechanism, kind of no joints in it, obviously, that's fine. And then we say okay. All right. Now, here is a torque law excitation. See that? Torque law excitation. You click on it. Okay, it says where's the support? The support is that entire object. Okay, you also need to select this application point. So I'm going to select this point, but I will show you later on that this point, the position of it, it makes no difference. Direction is going to be that Z axis. This is why I created that coordinate system up there, because I don't have any straight edges, otherwise I would have taken it. But the value of the torque is 200 Newton meters. So we go here, 200 Newton meter. Incidentally, if you have to put a formula for the value of the port, right click, edit formula. Okay, but mine is constant. I don't have to do that. And then I say, okay. Now, let me create a probe at that location because I want to plot the angular velocity based on my probe here to make sure, in fact, that I get what I want. So position and speed and acceleration sensor. So you select that point, okay? And then you say, okay, good, you're pretty much done. So now we can create our dynamic scenario. Remember, I created a torque law excitation. I created a probe, send it to the right-hand side. Parameter, let's do it over a 10-second interval. And this is fine. Say OK. And there are two algorithms here, solve integrators here. It makes no difference which one you use. I'll use the second one. In an earlier video, I think it was video maybe 6 or 7, I showed that you got to be careful about sometimes if you're involving elastic impact or coefficient of restitution involved, you have to change this thing. But that's okay. We don't have any of those here. Say all right, and then we're gonna simulate 10 seconds. Okay. Uh, I just noticed that I did have another scenario here, but actually this is the one that we are using here right now, scenario 2. Okay, good. So results, just give it a second. Okay, deselect everything. Let's plot a few things. First of all, let's look at the torque value. Z torque, it should be 200. 200, you can see that. Apply torque. Let's plot the acceleration. Angular acceleration about the z-axis. That better be, oh, sorry, this is angular velocity. Let's look at the angular acceleration about the z-axis, which is right here. That should be 40, 40-ish, 42, right? These are all things that I did the calculation. 41.95, okay, good. Now let's look at the velocity. Check that, angular velocity about the z-axis right there. And that better be the linear variation to 4,000 RPM. You see that? 0 to 4,000 turn per minute, which is RPM. Now, next thing I want to show you is that the position of this point makes no difference in this problem. So if you go to point number 1, just literally move it somewhere else. For example, maybe move it to also x of 0.5. 0.5. There. Okay, so it's not directly on that axis. So let's go back to our scenario and run it. The only thing that I did is the position of that point. Okay, let's plot our stuff. Okay, plot. Okay, and deselect everything. Let's look at the angular acceleration. That better be 42-ish, 42-ish. Let's look at, for example, the torque, z-axis. That better be 200. And look at, for example, angular velocity. Here's the angular velocity. It's that linear variation from 0 to 4,000. However, what I'm going to do now is I will change the direction of the rotation. So we go back here. So let's go back to that torque law excitation. Instead of z-axis, I will choose a different axis. So let me see if I can I delete this line and then I select my z-axis. The only thing is that let me hide that. Can I do the y? You have to select the axis. So I'm having a hard time. I'm having a hard time selecting these from the screen. So what I'm going to do instead, I'm going to use this coordinates. I'll make this thing in the direction 1 and this thing direction 0. Okay, I had a hard time picking that axis. All right, so now let's go and simulate. So it's not the problem that I want, but let's see whether actually that's reflected here or not. There. That's not what we want. All right, let me stop this thing. Well, I mean, obviously you're not going to get what you want, but I would like to plot some results too. Nonsense, this is not my problem. So for example, if you plotted rotation about the z-axis, it's going to be all 0. But there's no rotation about the z-axis. Rotation, angular velocity about z-axis. Yeah, it's not what we want. All right, folks, so good luck.